Okay, so thank you very much. Thank you for coming. This is Kalpana Singh, and good afternoon, everyone. I'm working at IRT SystemX as a cybersecurity research engineer. I'm basically working on cybersecurity and blockchain projects, and my job is to provide solution using applied cryptographic protocols. So we'll see today some use of cryptographic mechanism. Maybe you heard somewhere the use of the data privacy, information security, and how we can provide solution for cryptocurrency wallet security problems. Basically, we are going to see the use of threshold ECDSA. This is one of the cryptographic protocols, and we'll see the use in cryptocurrency wallet security solutions. And this is a joint work with blockchain Additive and IRT SystemX. So this is the agenda of my talk. So I will introduce the subject firstly, why threshold ECDSA is important in the context of cryptocurrency wallet security. Then I will talk about some cryptographic primitives which has been used in our solutions. And this work already been submitted to Crypto 2022. And we'll talk about some existing solutions, and we'll talk about the problems, which is basically research problem to us. And then we'll talk about I will talk about the solutions and our results, what we have obtained so far from this analysis, and what we are doing at the moment, which is next not the next, but is ongoing work, which is proactive refresh and interoperability solution. And if you'll not get it the point, the word is not problem. I will cover all these terms in my coming slides. So basically, I will start a scenario where the words like cryptocurrency transactions, privacy, and the keys would become. So basically, in a scenario here, a user A wanted to send some blockchain using the blockchain transaction, some bitcoins to user B. There are some keys. You could see that PKA, SKA. So these are public key and secret key for each user, because this is based on one of the primitives of cryptography, which is asymmetric cryptography systems. I will talk about these keys in my next slide, why these keys are important and what are the meaning of these keys. Yeah, so we'll consider this scenario where user basically using a secret key for signing the transaction. When it is authenticated, it will go to the blockchain and then would be accepted by the user B. And how the user could verify, because of the public key of the user A, he could verify the transaction and then accept the transaction. Just to imagine, so here the process of the public key and private key is very important in the context of cryptocurrency wallets. So when we generate in cryptographic key, basically everything is come with the random numbers, and it is based on one of the technology which is called Galois field, but I'm not going to explain here Galois field, but it is just only the random number, integer random numbers. And we use some algorithm, then we would have two kind of keys, public key and private keys. So private key is really very important, because if you see, you are using banking transactions, social networking site, everywhere we use cryptographic protocols, and mainly we use asymmetric cryptography, where we have public key and private key, and we never lose our private key. And in blockchain, it is really important, because when you lose your private key, you will lost all your money. So it's very important how to manage your private key. And then public key is basically for blockchain. It is address. It is wallet address. And when you are sending any transaction to anyone, the people could verify by seeing your public key, which is your address. So if you take an example of Ethereum, you see the Ethereum address, that's basically your public key. So anyone can verify from your public key, and it is known by everyone who is participating in that particular transactions. So these are key, very important when we are talking about cryptographic solutions. So going back to the first scenario. So just to consider, when user A wanted to send some bitcoins to user B, just imagine that when the laptop or the devices which has been used by user A is being hacked. So how, because all the keys it has been stored on one device. So when it has been hacked, so all kind of malicious activities could be happened with by the attacker, and that's a real problem in management of the private key when we are talking about decentralized solutions. So what the user A could do, the user A could basically the simple approach. What he could do, he could divide his private key into let's say two devices. He could store one fragment of key in one device and another fragment of key into the another device. And if attacker could have the one fragment of the key, he cannot basically sign the transaction because of the security proof of the cryptographic primitives of digital signatures. So this could be a solution. And maybe you heard about multi-signature, because bitcoins is using multi-signature, and that they are using somehow similar to that concept. But the problem is here there is no anonymity. So in multi-signature, if we use the multi-signature concept, so there is a specific structure to sign your transaction, and that structure is visible to everyone. So this is a real problem when we are talking about the anonymity, because no one wanted to disclose their identity to to Bitcoin transactions, because it is a public, and anyone can see by seeing your transaction, anyone can trace your identity and the behavior of the users. So, and the second problem is, for signing a one message we need many approver to sign that transaction. So for example, if it is a board of directors wanted to sign one message, then we need all the board of directors, let's say 10. So we need public key and secret key for everyone. And sometimes we really don't need that kind of unnecessary data, because in blockchain when the data is there, is always be there, we cannot revert back the data. So that's why the use of multi-signature has not been preferable by the industrialists and also the researchers. So what we could do, if we are not going to use multi-signature, then we'll come about threshold signature. So in threshold signature, I just gave the example of the board of directors. So if we have 10 directors, we if two directors are available, then it is okay to two directors could sign by using this kind of mechanism. So what it is, this mechanism is, in this we do not need the secret key and public key of each individual. We need only the share of the secret key. So for example, if we have secret key ska, we are considering an user example. So we can divide the shares of the secret key, and then we transfer these shares to different devices. And two or it depends on the protocol basically. So threshold cryptography is very rich in terms of protocols. So it depends on which kind of protocol you are going to use. So if we are using the standard one, the notion is t comma n. So t is basically less than of n, and t plus 1 people could make a signature, and that could be verified by everyone. And here we follow the anonymity property, and we also follow the property of redundant attributes, which was the case of multi-signature. So and also it has very high level of security as well. So this is just an example. For example, is t comma n. I just gave an example. So any three party could sign a transaction. There is no need to be available all the people at the same time to sign a one message. So any three party. Why? Because this is a cryptographic protocol threshold. And the standard protocol, I just gave an example of t comma n. So here t is 2, and it cannot be less than 2, and n is the number of the participant, let's say 5. So t plus 1 is mandatory to be available to sign one transaction. So any three party could sign a transaction. Yes.
And in this case, how does the public key work? Because do you need to have a public key for each pair? Or?
No, so there is one public key and there is one secret key, and we share only the share of the secret key.
And you can use only part of the secret key to sign, and it is enough. The public key will be able to verify that.
Yes, yeah.
I didn't know that.
Yeah, so this is the use of threshold signature instead of multi-signature. Yeah, so for example, if it has been hacked by more than two systems, so you are not able to sign a transaction. So here threshold cryptography follow the fairness property. Fairness means that if honest people or honest participant is not receiving the correct output, then malicious people cannot. So this is a fairness property, and it has the notion of threshold cryptography. Threshold signature has this notion, so it is another advantage of using this threshold cryptography, threshold signature scheme. So then we are talking about ECDSA, because ECDSA has been widely used by Bitcoin, Ethereum, and Tezos, and these are the blockchain technology. Normally, people use it for their business transactions. There are some others like Solana and the Monero. These are the permissionless blockchain system, but normally prefer these one because it has a lot of use cases which has been used by industrialists. So that's one of the reason we have focused on ECDSA. So ECDSA is based on curve, and it is elliptical curve cryptography. This is one classification of cryptography, and it has been standardized by NIST and was proposed by David Kravis. And it has been widely used by most of the uses of the internet cases, such as transport layer security, domain name system security, and secure socket layer, and so on. So that's why we have focused on ECDSA and trying to achieve threshold ECDSA. But the problem is with ECDSA is that it has non-linear equations, and in threshold cryptography, you could achieve a threshold system if you have linear equations, because it has some restrictions, because you cannot get everything in one hand. So there is some restrictions. So how you could achieve non-linearity with threshold friendly nature? Before going to into the deep how we could achieve that, I just wanted to explain what is a signature, because I'm using every time signature. So we saw that the private key and public key, how we could generate a signature, are very basic steps in cryptography. So initially you will generate the keys. So there is a key generation process, so where you generate secret key and public key. So SK is a private key and PK is public key. And this is a notion of asymmetric cryptography. For symmetric, we are not talking about the symmetric here. We are only considering the example of asymmetric, because symmetric is totally different. And then when you generate the keys, then you will have to sign a message, and you need secret key. So only the legitimate user could sign a message. No one can else sign the message, because private key is very so it's very legitimate candidate, you could say. And for the verifying, anyone can verifying by seeing your signature and the public key. So this is a basic concept of any kind of digital signature scheme, and it will depends in terms of the algorithm. It depends what kind of signature mechanism you are going to use: threshold, multi-signature, or threshold ECDSA. But this is the basic concept of digital signature mechanism in cryptography. So what is the problem when I said that it is not easily to become a threshold ECDSA? The problem comes here. So when we sign any message M, so we need secret key, and we have secret key and message M, and K is any random number. It is integer random number, and this is some. So here we have and some steps here. So basically these are the steps to make a signature. But the problem is here, you see, this is not a linear equations. And so people use another kind of DSA signature mechanism, which is EDDSA. So I will not talk about EDDSA, but EDDSA has a linear property which is easier to use. But the problem with that, there is the patent for EDDSA has not been verified or has been abandoned. So there is some problem. So we are obliged to use this ECDSA signature mechanism. And because of this non-linearity property, it is a problem to become a threshold ECDSA. So I'm going to introduce some cryptographic primitives, because these primitives are important to understand the literature of threshold ECDSA. So I will not go very much detail, but if you have any question, please do not hesitate and interrupt me anytime. So there are some cryptographic notions we must to recall those notion to understand the protocols of existing solution and our solution as well. So there is a additive secret sharing mechanism. So as a name, you could see the additive secret sharing. So you need to share your secret. So basically your private key, you need to share your share of your secret key in an additive manner. So there are some operations we use and those operations are addition, and we can distribute the share of the secret key, how many participants we need. We can define those participants, and then we can share the secret key by using this additive notions. And this kind of protocols has been widely used for joint accounts, or when we do the voting, so we need absolute votes. So this kind of solution can be useful for those applications. And so this is just only mathematical, the notion how we share the key. So it's only the addition property of secret sharing. Then this is a Lagrangian interpolation, and this is important to understand for another kind of secret sharing scheme, and we use that secret sharing scheme for our protocol. So that is Shamir secret sharing. Is Shamir is the name of a person who invented that particular secret sharing scheme. So here what we do, that we use Lagrangian interpolation, and what we can do that we have one, for example, this equation. So here a0, so it follows an algorithm. So a0 would be the secret key, and it depends how many participants we have, then we can follow some random value, and then we use the Lagrangian interpolation to see the points. So all the participants are the points, and then we use the Lagrangian interpolation to share the secret of the data. I know it could be tricky to understand in one slide, but that's I think I could say the maths. We use Lagrangian interpolation to calculate the random value, and then we distribute the share, and then we calculate the average, and and then we can see the answer. Maybe I could explain by an example if you're interested. So here Sami secret sharing scheme, that's why I explained Lagrangian interpolation, because we use those notion here. So for example, if we have 5 participants, and sorry, if we have 5 participants, and let's say this example, and we are using t comma n threshold signature scheme. So we have t is 2, so t plus 1 participants we need. So we can see any 3 parties, and then we use this equation with all these parties, and then calculate Lagrangian interpolation only with these parties, and then can get the secret key to sign a message. So this is very novel cryptographic algorithm, and most of the people use this Sami secret sharing approach when they are talking about to share the secrets, or to share the use of threshold cryptography. So they have to use this kind of notion, because this has been widely used in the literature part. So, and then we have another.
Yes. I have a question on this scheme.
Yes.
If the 3 people share the information of their part of the secret key, they can reconstruct the full polynomial.
No, for example, I can give an example. For example, 3 employee, they wanted to calculate the average of the salary, but they don't want to exactly share the salary. So how they could do that? So I could give an example. It is an average calculation. So for example, one employee has 200,000 euros. So it could divide one share, so such as 80, 30, and 50. Any random share. The second would do the same, and the third would do the same. Then they will use additive secret sharing. So basically they calculate the average, and what you will get on the average, they will calculate again the sum of everything, and then divided by 3, and then you will get that each employee would have then average salary. So they didn't disclose any information, but they get the average of employees.
My point was not on this
Okay.
aspect. It was more on the fact that if each member has a part of a key, of the key.
Yes.
By this
Yes.
way,
Yeah.
But if they are malicious and they coordinate themselves, they can recover the full polynomial and know the keys of the others.
No, no.
It's something I am missing.
Yeah, okay. So no, definitely they cannot calculate any information for others. But the problem is this protocol will be abort because they are not able to sign a transaction. Yeah, so basically I think I will explain in my coming slides. So it is honest majority setting where we believe that the people are the trusted, or they are adversary, but they cannot change the protocol. So this is based on honest majority assumption, this particular protocol.
Sorry, may I ask a little comment?
Yes, please.
I just read the page about Shamir secret on Wikipedia, and so if I understand well, the goal is rather to protect, say, a file with a key that is scattered among a set of users that you trust.
Yes.
And you want to be able to decode this file if you have enough participants. And
Yes.
so the key idea is, for example, if you assume that 2 participants are enough, so this defines 2 points. 2 points defines linear equation, and so you can do an interpolation. And so if you pick an arbitrary point on this affine equation, so you can verify that you have enough people. And so if you want more people, you just take a more evolved polynomial. Is it correct or not?
So it depends on what so if we are talking about Samish secret sharing, very standard one, the basic one, yes, it is correct. But now you cannot use that Samish secret scheme directly with the current scenario, because it has been attacked. There were some attacks, and now we have the new notion of Samish secret sharing. But what you have explained, that is the basic notion of Samish secret sharing scheme. Yes.
Okay, and so your goal compared to the basic sham, what is the gap between what I described and what you want to do?
So I wanted to use this sharing just to this is one part of the protocols. What I'm going to explain, I will use this concept just to distribute the key. But then I will talk about the signing the key, and how we can generate the distribution of key into 2 parts, which I will explain, I think, pre-signing and signing. So this is one small notion in our protocol. It's not complete. Our protocol is not directly based on this. These are the primitives we have used in our protocols, and the goal is only to manage the distribution of the keys.
And just to be sure to understand, what is the gap provided by your protocol compared to Shamir secret approach?
So so our protocol basically, the threshold ECDSA. So we, as I said, we are using these primitives, but this is not a complete protocol. The protocol I will explain in my coming slide. So what we have difference from our solution and from the existing solution, I think I will explain in my coming slide. It would be more clear if I will explain here.
Okay.
Maybe get confused.
Okay. So please go ahead.
Yes, please. Thank you. So this is another notion, and we will use this notion as well. And this is called multiplication to addition share conversion. And we used this property in computation of the inverse multiplication, where if you remember, I explained ECDSA signing. There is a inverse multiplication. So we use this property to become an addition, and then we can share the secret of the key. So this is another cryptographic properties we use. So what it is, so here you can say it's normally 2 additive secret sharing schemes with Lagrange and Shamir secret scheme approach, and we wanted to this additive secret share. So it's basically multiplication of this one, and then we'll get the summation of the values. And this property we could achieve by homomorphic encryption. If you heard about it, very in summarizing manner, homomorphic encryption is when you encrypt any value, you don't want to see the original data, but still you can perform the computation on encrypted data, because of homomorphic encryption has some properties. And so I will not explain those properties here, but it's because of homomorphic encryption properties. It has both properties, additive and also multiplicative, and we use this notion to achieve the multiplicative to additive share conversion protocol. I'm sorry, I know it's a little bit scattered, but we use different cryptographic protocols to achieve one solution. So I need to explain what kind of protocols we have used. So we saw the Sami secret sharing approach, and then the use of multiplication to addition share conversion using homomorphic encryption. And so how we could exchange here, for example, this is the player pi and player pj, and definitely player pi has xi is one of the secret value, that is the random value, and pki is the public key and the secret key of the player pi. And the same for this is not our this is the one of the existing concept, it is not our solution. So we use these notion in our solution. I wanted to just clarify that. So it is not our solution, this one. So multiplication to addition exchange protocol. So they used this kind of random values, and then calculation of these value. What it is important to us, then when they share two multiplication value, how they could compute just by adding the values. So here they use Sami secret sharing approach, additive Sami secret sharing approach, and homomorphic encryption approach. So this notion is important for us when we'll provide our solution. So these four cryptographic notions we use in our protocol. And in my next part of the talk, I will explain very briefly what kind of solution is already there and what is the research problem for us, and then our solution part. So this problem has been arisen since 2018, and people started to talk about threshold ECDSA because of cryptocurrency wallet security solution. And if you see, there are some parameters here, majority, adversary, okay, so okay, I don't know this one's cursor here. So if you see, there are columns, majority, so dishonest, and honest. So basically this is a cryptographic setting. When we say is honest majority, it means the people or the participants who are participating in the transaction, they are honest. Sometimes they could be semi-honest, means they can see the protocols, but they are not allowed, they cannot change the protocols. And dishonest is very strong cryptographic notions. It means that the participants who are participating, who can be attacker, but still the protocol is running. So this is really a strong notion of security in terms of attacks. So then adversary, so it's static and passive, and sometimes you maybe listen about active and passive attacks. So passive attacks, there are so the attacks who can involve as a participants in the cryptographic system, but they cannot change anything, and they will just sit and just observe the protocols, and that's it. But if it is active attack, they can do anything. They can change your the message, they can change your keys, they can steal the money, anything that could be happen. So this kind of solution are only good for the passive attacks. If there would be any active attack, then all the solution would not be supported. And then here is assumptions, because they have used cryptographic protocols, as we have used for notion, Sami secret sharing and so on. So they have used their algaml, and these kind of cryptographic, there is a big list of cryptographic protocol they have used for different papers. So we analyzed all these papers, and then the other papers, we analyzed these 2020 papers basically, and there were 5 papers. I listed here 4 because one of the paper is not very much important to us. So we analyzed all these paper, and then we find one basic problem in all these existing solution. So what is that problem is, when in threshold signature, when the signers is going to sign, they know the signer in advance. So for example, if all the people are living, one in France, one in India, one in Canada, and it is not possible to everyone to be available at once same time and to sign a transaction. When we have that kind of use case, then how they could provide a solution. So that's basically the goal of these kind of existing solution. And all those solutions have been based that they know the signer in advance, And because when they are signing, so they have the steps basically. So the one is distributed key generation, then is signature, and then verification. So in the signature part, they do the pre-signing and signing, and all are based on this kind of issues. So we try to solve this problem and with the same communication cost. So we didn't increase the communication cost, and we also solve this dependency problem of the signer. So we propose basically two solutions. The one solution is to solve the problem of pre-signing, which means that we don't need the signer in pre-signing phase, but we know the signer at the signing phase. And signing phase, it could be one step or two step basically, because we are doing on the blockchain. Then we propose another solution where we don't need the signer, we don't need to know the signer in advance, either in pre-signing or signing. So this is our contribution in regarding threshold ECDSA solution. So we generalized this Gannaro and gold feather. The reason was that this was the very recent work, and it has a good notion of the communication and computation complexity, and it is also open source. So if you wanted to use the code, you could directly use the code and to modify your code. So and the guy is very active in threshold ECDSA problem. So we took this problem Gannaro and gold feather, and we analyze this scheme, and their scheme is also based on say multiplication to addition approach and Sami secret sharing approach and so on. So you see, we need a key generation step. So here is not the detail of the generation of keys. If you are interested, you can check his paper, but it is very good written and very understandable. So we need to generate the keys here, and then we have the pre-signing. So when we talk about the pre-signing, we have several interaction, which means that we need to communicate many people who are participating in the transaction, and then we know the signer who are going to sign for the for the final signing stage, where we know the message. So it is very important step in the signing. We must know the message before final sign in step. And then here you see they calculated the threshold ECDSA value. So they are showing that the ECDSA could be calculated using a threshold manner. And this solution is also open source. If you wanted to try, you could try. And so we use this paper as our base paper, and most of our protocols, the cryptographic primitives are based on that paper. So as I already explained, what we have done, we solve this dependency problem of the signer, because we are working some use cases where we don't need that dependency, and we need to solve that dependency. But in cryptography, if you change one parameter, all the algorithm or all the mathematics would be very complicated. So I will show the benchmarking results, but for the small numbers it is okay. But when we increase the maximum number of more than 10 participants, our scheme has some communication issues. So but for the small number of people, like 10 people or less than 10 people, or maybe 15-20 people, it is okay. So we solve this problem, and this is the results. So it is not the results at the moment. So basically, why it is need to solve this dependency problem, because in threshold cryptography, when we have t comma n, so it's when it is minimum people, it is okay to to know the signer in advance. But when we have so many people, like 50 out of 100, or maybe 25 out of thousands, then we need to calculate several parameters, and it is not good to know the signer in advance, because you have to compute the secret key and public key with every 1,000 people. So it is very good to have to solve this dependency problem of the signer. This is one of the advantage and a strong reason that our solution is more feasible than existing approaches. So we proposed two solutions, as I explained. We named late roll call and without roll call. Late roll call because we solve the problem of the pre-signing. So in pre-signing stage, we our signature is independent in the pre-signing stage, but in the signing, when we have single transaction on the blockchain, that time we know the signer. In the second solution, we have complete independency, and we also we also have the open source. If you wanted to see our result, definitely you can try from the source code as well. So I just here the briefly summarize what we have done, but it is very complex in terms of algorithm. We already submitted a paper. If you are interested, definitely I could share with you. So we have the same steps of key generation and pre-signing and signing. The idea is we just only yes, manage this the dependency problem, and we were able to manage just because of homomorphic encryption properties. So this is a result. So we did compare with Ganero and Goldfeather, and BS21 is our work and GG20 is their work. So here, if you see that when we have participants, because we tested for 10, but when we go after 10, our the cost at the pre-signing stage is going to increase. But it is not important because pre-signing is offline phase, and signing is important, which is doing in the the real blockchain transaction. So these are the other results. If you see here we achieved the same communication cost with the Ganero and Goldfeather in the signing transaction, which is more real application. So that part is already been done and submitted in a conference. And what we are doing now, if you remember, just going back to the first scenario where we're talking about this one. So what we are doing here, as I explained, all these existing solutions are working for the passive attacks. So what would happen if the attacks would be the active, which means that the attacker could have your keys in according to the time. So for example, on 16th of March today, the user would have two devices, and the attackers could have the one of the device. So it is okay if you apply the threshold signature, and then for 17th of March, the user could restart everything. And then he said that okay, now it is okay. That is called the proactive security approach. And here user is doing the key refresh. But again on 18th of March, the attackers could hack the another device. So basically attackers here trying to add the dimension of the time. So the logic is, if you have one complete threshold, in complete one threshold, if the attackers can hack all the devices, let's say you can code it like one day or maybe 1 week or maybe 1 hour. If in 1 hour attackers could hack all the devices, that kind of solution would not work. So what we have studied will not work. But it is not possible, because the attackers is when you give the time limit, then we have approach which is called key refresh management, and here we are working on it. So what we do it here, so in every stage, so for example, here we have the share of the secret key. So we are not using one devices just to store the complete key. We store the share of the secret key, and then for the next day we'll restart the system, and we will generate a new share. But that share, the computation of the share would be the same private key. So, and we'll do the same for the another day. So if the attacker is getting some information in one threshold complete time, he would not be able to get the complete information of the private key. So this information is called key refresh mechanism, and we are trying to introduce in our in our solution what we have achieved in threshold ECDSA. So we are here, and I'm finished now. So we are working on here. So thank you very much.
Thank you.
Yeah, thank you. Have any questions?
Any question in the room or in the bridge? I have one question on my side. So you are working on this kind of mechanisms for with shared keys.
Mm-hmm.
Do you or SystemX, do you participate to some standardization on this aspect, or do you contribute to standardization?
We didn't contribute on standardization, but we work like that with the clients. So if the client says the problem, so we work on proof of concepts. So we demonstrate what we have done. So yeah, so we work in these aspects, but not the standardization. But we submit the papers in conferences as we did.
And when you say, I don't know if you can say it or not, but if you cannot say it, it's okay. I am Nokia, so I know sometimes we cannot say everything. Which client it is?
Yeah, it's Cash the Depot. I think Cash the Depot, CDC and Blockchain XJ. So basically, we are working with the Blockchain XJ, but we are working for CDC people.
Questions? So thank you again.
Yeah, thank you.